Large-scale human-labeled data has been at the heart of some of the most significant advances in domains like computer vision and NLP, enabling machines to achieve human-level performance on image recognition and question answering. Human demonstration datasets can also endow robots with impressive manipulation capabilities. For example, demonstrations provided via virtual reality or phone teleoperation can result in robots being able to perform various tasks autonomously. This is still far from human-level manipulation. What has inhibited the use of large-scale human data to address this gap? Here I'll discuss 5 challenges that make this setting difficult. Humans are not perfect Markovian agents. In addition to what they currently see, their actions may be influenced by other external factors, such as the device they are using to control the robot, and the history of the actions that they have provided. Collecting data from multiple humans can also result in mixed quality data, since some people might be better quality supervisors than others. Policy learning is also sensitive to the state and action space coverage in the dataset. Unlike traditional supervised learning, where validation loss is a strong indicator of how good a model is, policies are usually trained with surrogate losses. This makes it hard to know which trained policy checkpoints are good without trying out each and every model directly on the robot, a time-consuming process. Finally, performance can be sensitive to important agent design decisions, like the observation space and hyperparameters used for learning. Despite all these challenges, studying this setting could be a stepping stone to realizing the promise of large-scale human data for robotics. Therefore, in this paper, we conduct a study of offline learning from human datasets in order to investigate and potentially address the challenges from the last slide. We then present lessons from our study in order to guide future work. We will also release all code and datasets to facilitate future work. The study consists of 8 tasks, 3 types of datasets, 6 offline learning algorithms, and 2 different observation spaces to thoroughly investigate the challenges mentioned earlier. In this study, we collected data on 5 simulation tasks. These tasks were chosen to test a broad range of manipulation abilities. Lift and can consist of simple pick-and-place motions. Square consists of fitting a square nut onto a peg, which is substantially more difficult due to precision needed for insertion. Transport consists of a task where 2 robots must work together to retrieve a hammer and transport it to the other side. This is challenging due to the multiple stages, each requiring different levels of coordination. And finally, tool hang, where a robot must assemble a tool stand and then hang a wrench off of it. This is the hardest task due to the multiple stages that each require precise and dexterous rotation-heavy movements. We collected 3 kinds of data sets in the study to isolate what makes learning from single and multi-human data special. Machine-generated data consists of suboptimal, expert, and random agent rollouts. This provides a comparison with mixed-quality human data. Proficient human data consists of 200 demos from a single human. This is common in imitation learning. The multi-human dataset is collected by 6 humans of varying proficiency, resulting in mixed-quality data. We evaluate 6 offline learning algorithms in our study, 3 imitation and 3 offline RL, behavioral cloning, BC with an RNN network to model history-dependent reasoning, a hierarchical variant of behavioral cloning, and 3 state-of-the-art offline RL algorithms. To study the effect of observation space, we train 2 kinds of agents, low-dimensional agents that have ground truth, and image agents that receive camera observations. We now summarize the lessons from our study. We saw that history-dependent models can be an effective way to deal with challenge C1 and are extremely effective on human datasets. Next, we investigated the ability of algorithms to deal with mixed-quality multi-human data. We found that while offline RL is great with mixed-quality machine-generated data, it struggles with suboptimal human data. We saw that challenge C4 causes problems for policy selection. Unlike supervised learning, the best validation loss does not correspond to the best performing policy. The best validation policy is 50 to 100% worse than the best performing policy. Thus, each policy checkpoint needs to be tried directly on the robot. This can be costly. When investigating C5, we found that observation space choice and hyperparameter selection is crucial for good performance. As an example, not including wrist camera observations can reduce performance by 10 to 45%. Finally, studying how dataset size impacts performance made us realize that using human data holds tremendous promise. For each task, the bar chart shows how performance changes going from 20% to 50 to 100% of the data. Simpler tasks like lift and can require just a fraction of our collected datasets to learn, while more complex tasks like square and transport benefit substantially from adding more human data. Furthermore, we were able to train a proficient image-based agent on our hardest tool hang task. Together, these results show the potential of large human datasets as a means to solve challenging and complex manipulation tasks. Finally, we show that our study insights can directly transfer to real-world settings. These BC-RNN policies were trained using 200 human demos. No hyperparameter tuning took place here, and we report the final policy checkpoint performance instead of the best one, since evaluating all policy checkpoints on a real robot is time-consuming and infeasible. Tool hang is likely much harder than in simulation, but the other tasks roughly match simulation performance. We saw some common failure cases for tool hang policies in the real world, such as missing the insertion, failing to insert the rod, failing to grasp the tool, and dropping the tool instead of hanging it on the rack. There is substantial room for improvement on this task. As in simulation, we saw that both wrist images and pixel shift randomization is crucial for good performance. See our paper for more experiments and a more comprehensive discussion. See our website for more qualitative results.